So these triacylglycerols undergo chemical reactions. One of them is hydrolysis. We've talked about this in organic chemistry section. Hydrolysis is the reverse process of esterification. So we saw how the triacylglycerols are made by the trialcohol glycerol reacting through an esterification reaction with the carboxylic acids. And this is just undoing that, taking it apart. So what happens in the laboratory is there's two different ways to hydrolyze these triacylglycerols. One is in an acidic environment, and that's going to produce glycerol and fatty acids. Or we can do it in a basic environment, and this is called saponification, and we've talked about that before. And here the product is glycerol again, but now we get fatty acid salts instead of the actual fatty acids. In the human body, the hydrolysis is catalyzed by enzymes instead of by an acid or a base. So the enzymes catalyze it, and it occurs stepwise, meaning first one fatty acid comes off, and then another fatty acid is taken off. And oftentimes it just removes, your body just removes the two fatty acids on the outside and will leave the one in the middle. So the outer fatty acids are removed first, and oftentimes it leaves this monoacylglycerol. And so we refer to that as partial hydrolysis, because it hydrolyzed two of the ester bonds, but not all three. So here's an illustration. So here we have a triacylglycerol. There's the glycerol backbone, and here's the ester bond, and we've got our fatty acid residues over here, our acyl groups. Is this one a mixed or a simple triacylglycerol? This is mixed because these groups are not the same. So when we do complete hydrolysis, and this is in an acidic environment, what happens is we're adding water back into this ester bond. And so the water adds between the oxygen and the carbon, and we get back the glycerol and three fatty acids. That's what would happen in the lab. In your body, what's more likely to happen is partial hydrolysis, and this is catalyzed by enzymes. And so the enzymes will catalyze the hydrolysis of this fatty acid on the end and the fatty acid on the other end. And so you'll get two fatty acids, and this would be called a monoacylglycerol because it's glycerol with one acyl group on it. And that's partial hydrolysis. And that's more typically what happens, and this would happen during digestion. You consume dietary fats, and what does your body do with them? Well, it breaks them apart so it can move the pieces around and use them to make other things. Your body really is just this big recycling factory. So, writing a structural equation for the hydrolysis of a triacylglycerol. Write a structural equation showing the acid-catalyzed hydrolysis of this triacylglycerol. So this is just like the picture we looked at. So what's going to happen is we're going to have a water molecule come in right there. And hydrogen is going to go on that oxygen, and the OH is going to go on the carbon. And that's going to happen for each of these, because the acid-catalyzed hydrolysis is going to be a complete hydrolysis. So this would be plus, we're going to need 3 water molecules, and then what are we going to get? We're going to get glycerol, CH2, OH, CH, OH, CH2OH. And our other products are going to be fatty acids. So what do we have here? 1, 2, 3, 4, 5, 6 peaks. 1, 2, 3, 4, 5, 6. And then this guy on the bottom is bigger. These carbon chains aren't changing. All that's happening is that we're breaking this bond. How many is that? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I was just counting the peaks because it ends up being less counting, which is good. So that's what you would end up with. Any questions? So this is that reaction that we learned in organic chemistry, and now we're just applying it to this biochemical molecule. Another reaction is saponification. And this is just the hydrolysis in basic solution of these triacylglycerols. And so we can think of it as happening in 2 steps. This is how I prefer to think of it. You've got the fat or oil, and you hydrolyze it. Just like we saw, we get 3 fatty acids and glycerol. Well, these fatty acids are carboxylic acids. If this is in the presence of a base like sodium hydroxide, what happens to the acids? They become salts, right? This OH group will pull the hydrogen off of the fatty acid part. So let's see. So here you have the OH, that's the base. And here you have your fatty acid, however long it is. This hydrogen is the acidic hydrogen of that carboxylic acid. And that is going to come over with the water. And then what do we have left? We take that guy off, and now we're left with a negative charge here. And we've got the sodium ion from the sodium hydroxide. And so we get a salt. And we've seen this before as well. Saponification is the process by which the pioneers made soap. So, they ate meat. They either, raised their own meat or they went hunting. And they saved the fat and they heated it with lye from the ashes of the fire. And that wood ash is actually an impure form of potassium hydroxide. So if you heat the lard with ashes in it, you can make soap. Now, is that a beautiful, pretty smelling soap that we like to have? No, but it did the job. The way soap works is really pretty cool. So when you do that, you end up with these fatty acid salts. So here's what those fatty acid salts look like. They've got this carboxylate end that's an ion. This is very polar. And then they have this long hydrocarbon chain, which is very nonpolar. So they kind of have 2 personalities. And what they will do is they will form what are called micelles. They'll form spherical clusters, and on the interior of this will be all of those hydrophobic tails, those nonpolar tails. If there's any grease or oils around, the grease will be soluble and be happy in here. Grease isn't soluble in water. And the carboxylate ends of the molecule go to the outside because they can interact with the water. And so you get these little, very small micelles. And they've got this anion on the outside, and so they can move around in the water as small, small particles. And they basically will help to solubilize the grease and the fat. If you've ever baked and had to grease a cookie sheet or a cake pan with Crisco, you get Crisco on your hand. Can you rinse Crisco off with water? You can't. It does not dissolve in water. You could wipe it off with a paper towel and rub the rest of it into your skin, but the only way to get it off is to use soap. How does soap get the grease off? Well, this is what it does. The soap molecules will put all their little tails that are nonpolar, and they'll pick up little pieces of the grease or the Crisco, and that will be happy in here. And it's like it's cloaked in stealth mode, and then it can go out in the water because the outside of that micelle is polar and can interact with the water. Because normally, if you have oil and water, they won't mix up. But if you put soap in there, then they will mix. I think that's kind of cool. Another reaction that these can undergo is hydrogenation. And this is also one that we talked about in our organic chemistry section. So hydrogenation, to refresh your memory, adds hydrogen across carbon-carbon multiple bonds. We're not going to see triple bonds here, we're going to see double bonds. But what happens is, here is an unsaturated fatty acid with a double bond. Well, if the conditions are right for hydrogenation, one hydrogen molecule will add across that double bond and the double bond goes away. This is another one, and so it can hydrogenate all of those double bonds. And now we have something that is saturated. That's going to affect the melting point of the substance. Many food products are produced by partial hydrogenation. And if you're at all interested in nutrition, you've probably heard about partially hydrogenated soybean oil. And you've heard about trans fats, and there's all these words that get thrown around. It's all biochemistry. That's all it is. A partially hydrogenated fat is where not all of the double bonds have been hydrogenated, just some of them have. The problem with that, so here is a natural 18,2 fatty acid. These bonds here are almost always cis bonds in naturally occurring unsaturated fatty acids. When you partially hydrogenate it, you remove some of the double bonds, but not all of them. In that process, because of the catalyst that is used, what happens is many of these bonds end up opening up on the catalyst, and when they reform as a double bond, they can reform in either orientation. And so these cis bonds can be converted to trans bonds. And that's where we get the trans fatty acids, the trans fats. And we're recognizing more and more that those are bad. And one of the reasons that they're bad is, look, this guy with its trans fats has a very similar structure to this saturated fat, doesn't it? So trans fats are going to do much the same thing that saturated fats do. And just something to watch out for, if you see a food that's labeled 0 grams trans fat per serving, that doesn't mean that there are no trans fats in it. It means that there's less than half a gram. They round, right? They round. So it could have up to half a gram. The other thing is they don't count naturally occurring trans fats. And there are naturally occurring trans fats, so they're only counting the man-made ones. So, in my opinion, if you look on the label and it says partially hydrogenated anything, look for something else. Now, honestly, for pie crust, for Thanksgiving, I do go with the Crisco, which is partially hydrogenated vegetable oils, and I'm sure it's full of trans fats. But we'll survive doing that once a year. But I wouldn't want to use that on a regular basis. A lot of the fast food restaurants and stuff have gone to using different types of oils to avoid these trans fats. Because honestly, if you're going to end up with these trans fats that are just as bad as the saturated fats, why not just use lard? Why not? At least it's natural, right? That's my opinion. Another reaction is oxidation. Double bonds are subject to oxidation, and this can happen just with air. Oxygen in the air can oxidize these double bonds, and so you can end up with short-chain aldehydes, and those can oxidize further to short-chain carboxylic acids. Many of these carboxylic acids, and especially the aldehydes, have odors that are not pleasant. And so I don't know if you've ever encountered this, but you open something that has oil in it and it doesn't smell good. We say it's rancid. And what's happened is that the oils and the fats in it have become oxidized. To avoid that, many foods that are processed have antioxidants added as preservatives. And what an antioxidant does is it gets oxidized instead of the fatty acid being oxidized. So it's basically, I just lost the word. It's like a sacrificial molecule. It says, here, oxidize me, leave the fat alone. So there's natural ones. Vitamin C and vitamin E are good antioxidants. And there are also synthetic ones, BHT and BHA. We mentioned those earlier in the semester. Okay, determining the products for reactions that triacylglycerols undergo. So it says using words rather than structural formulas characterize the organic products formed when the following triacylglycerol undergoes the reactions listed. We're going to use words. We're not going to write formulas. So if this triacylglycerol is completely hydrolyzed, what happens when we hydrolyze it? We're adding water, and the water's going to add in here and break these guys off. And what do they become when they come off? And the fatty acids, right? So from the complete hydrolysis, we would get glycerol plus 3 fatty acids. And this is really more what we're interested in than in the very specific different molecules, because there are many of them and we don't encounter them singly anyway. They come all jumbled up and mixed together in their natural environment. We're more concerned with the overall idea of what are we getting. So what if we do saponification using sodium hydroxide? We're going to get fatty acid salts, right? Because this complete saponification using sodium hydroxide is the same as hydrolysis, except it's in a basic environment. And these fatty acids in a base undergo an acid-base reaction and they form salt. So we will also get glycerol, but this time we'll get 3 fatty acid salts. What if we get complete hydrogenation? What does hydrogenation do? It's going to get rid of these double bonds. Complete hydrogenation means they all go away. So then what's left? A saturated fatty acid, right? Because this one currently would be considered polyunsaturated, because there are 3 double bonds here. 2 on one and 1 on the other. So complete hydrogenation would yield a saturated triacylglycerol. That's one word, acylglycerol. Any questions?
So hydrogenation would turn it from a mixed to a simple?
It could turn it from a mixed into a simple. In this case it would, because all of these have 18 carbons. And what's making it a mixed triacylglycerol is this one has 0 double bonds, this one has 1, and this one has 2. So for this one, when we hydrogenate it, yes, it does become a simple triacylglycerol. All of these will then be the same. They'll all be 18 zeros. Now, if you had 18 0 and 21 and 24 2, and you hydrogenated it, you would still have a mixed one. It's a good question. Any other questions?
Why is that?
Hmm?
Why is that?
Well, because what makes it mixed is that these acyl groups are different. So if this one, instead of being 18, if this one was 24, 2, and this one, let's say, was 20 with 1, when I hydrogenate them, I'm still going to have different carbon lengths. And so it's still going to be a mixed triacylglycerol. Because for it to be as simple, they all have to be the same. And they can't be the same if they have different carbon lengths. Any other questions?
Since there is like two double bonds in the bottom one, would you need more hydrogen?
You would need more hydrogens. And what was important there, so if we can go back, is it does say complete hydrogenation. If it was partial hydrogenation, it would be hard to predict what would happen. You would get a triacylglycerol that is more saturated, but you can't really predict exactly. You could get some that are completely saturated and some that aren't. And basically, they just hydrogenate it enough to do what they want to the melting point. And so they'll take something that's a liquid at room temperature, a solid at room temperature, and they'll partially hydrogenate it. No, backwards. Brain's not working today. When you hydrogenate it, you get rid of the double bonds, and that allows the molecules to get closer together, so you have stronger intermolecular forces, and so the melting point goes up. And so what was a solid will become softer, will become a liquid. I have to think it through like that every time. Today my brain is very tired.